Hello, and welcome to today's Introduction to Hearing. In the next several sections, we're going to be talking about hearing, and to set the stage for that, it's important that we understand the physical basis for the stimulus for hearing, and that's going to be a discussion about amplitude, frequency, and phase. So some of these concepts we've seen before. We'll introduce them here now in the auditory context, and we'll see that there are some important parallels to the visual context that we had already completed so far in the course. So let's jump right in and remind ourselves about amplitude, frequency, and phase, and see how this is similar and also different from the way in which we talked about these constructs in the domain of vision. So we'll begin by talking about amplitude, and we'll remind ourselves that amplitude is the physical dimension of a wave that indicates the peak to trough displacement. So let's unpack that. We already have the introduction of a few terms that we need to understand very precisely. One of these terms is the term wave. As you might recall, a wave is a traveling disturbance, and we have all different kinds of waves. You might recall that when we talked about electromagnetic energy, which is a stimulus for vision, we talked about this notion of a transverse wave. In a transverse wave, the individual particles are oscillating in a manner that's perpendicular to the overall direction in which the wave is traveling. That's one type of a wave, the transverse wave. All light, all electromagnetic energy travels in accordance with a transverse wave. A wave is a traveling disturbance. We have other kinds of waves, other kinds of traveling disturbances, and these would include such things as longitudinal waves. And the auditory stimulus is, in fact, an example of a longitudinal wave. Acoustic energy is a longitudinal wave. In the longitudinal wave, we have local oscillations that are moving parallel to the direction in which the wave is traveling. So not a perpendicular relationship, but actually a parallel relationship. And in class, we'll do an example of the distinction between a transverse wave and a longitudinal wave. Here, when we're talking about the physical stimulation that gives rise to our auditory experiences, we're talking about these transverse waves. So the amplitude is the physical dimension of, in this case, a transverse wave that indicates the peak to trough displacement. In acoustics, the greater the amplitude, the greater the intensity. Okay? And we're going to see that intensity is one of two ways of measuring amplitude. There are other ways too, and we'll see those in just a moment. Here's a graph of two waves differing in intensity, differing in amplitude. What I'll point out here is something that's not labeled on the x-axis. Horizontally, we have the passage of time. It's not shown here, but in most graphs, when we're talking about hearing, usually the x-axis is about time unless otherwise specified. We have some indication of amplitude here on the y-axis, and what we've drawn are two sinusoidally varying stimuli, stimulus 1 and stimulus 2. They have the same starting point, as you might notice. They have the same frequency, and we'll be talking more about frequency in a few minutes, but you can see that they're reaching their peaks and their troughs at the same time, and as equally often in the two stimuli, for the two stimuli. But what you might notice is that stimulus 2 has a greater peak to trough displacement, and that is our indicator of amplitude. So stimulus 2 has a very large peak to trough difference. We have a more modest peak to trough difference in stimulus 1. So if you were to listen to these two stimuli, they would sound different from each other because stimulus 2 would sound quite a bit louder than would stimulus 1. So perceptually, the greater the intensity, the louder the sound. Okay? All right, let's see if we can understand where intensity comes from. When an object vibrates in a medium, say a tuning fork vibrating in air, it displaces air molecules nearby. So here again, we have to unpack something that doesn't appear directly in item number 2. And that is, we're talking about an object vibrating in a medium. Now, we make that point about an object vibrating in a medium because acoustic energy is a type of energy that actually needs a medium for its propagation. Sound does not travel through a vacuum. Light does, which is to say electromagnetic energy can make its way through a vacuum, but sound can't. Acoustic energy needs some kind of medium in which to travel. For most of our lives, the medium in which acoustic energy is traveling is air. But for other kinds of animals, like fish, the medium in which the sound is traveling would be water. And it's also the case that sound can even travel through solid objects. The more dense the object, the faster the propagation of that wave will occur. And so there is one number that I'd like you to jot down before we go too much further, and that is the speed of sound. Some of you might know the speed of sound by heart. For those of you who don't, the number that we're going to work with for the speed of sound is going to be 343 meters per second. I hope you'll jot that down. Again, that's 343 meters per second. Now to stipulate, that's actually the speed in air, and even more precisely, it's the speed of sound in a particular temperature of air and so forth. As the air gets more or less dense and the barometric pressure changes, then we get some fluctuation in that number. But we're going to go with 343 meters per second. If we were talking about the speed of sound in water, we'd come up with a different number. Speed of sound through a solid, different number, and that too would depend on the solid. Okay? So we now know that this acoustic energy is going to need a medium for its propagation. When an object vibrates in a medium, it displaces air molecules that are nearby. Okay? The displacement can be thought of as a local change in pressure, the number of air molecules per unit space. And here we're going to come to a different unit of amplitude. This is called pressure. It's going to be measured in a unit that you might know, the Pascal. And that is the same Pascal, Blaise Pascal, that you were introduced to maybe in your high school geometry course when you were learning about Pascal's triangle and so forth. The same French mathematician, philosopher, physicist that you knew from those days is back again giving us our unit of pressure. Okay? All right, let's see if we can understand this visually, and then we'll assign some numbers as we go along. Here's a simple tuning fork. Many of us are familiar with tuning forks if we've played various instruments. Some of us might be a little bit less familiar with a tuning fork. When you strike a tuning fork, it vibrates, and these are the poles of the tuning fork. They might vibrate outward, and then back to their center, and then inward, and back to the center, and then outward. And there's this cyclical pattern that we have of tuning fork vibrations. What we're showing over here would be different molecules of air, shown schematically. The filled molecules are the ones that are being displaced by the motion of this tuning fork, and the open circles are the air molecules that are not yet displaced, but will be soon as the wave begins to propagate. So let's see if we can draw our circle around a few of these, and we might take a circle around, or an oval around these two, and say that we have a relatively high pressure area here. So in this high pressure area, we have two molecules that are occurring in a relatively restricted region of space, really quite a small region of space. Down here, we have two molecules again, but the two molecules are now occupying a much wider region of space. So this is said to be high pressure, this is said to be low pressure. You might think of this roughly as being akin to something like a city's population density. Here we have a relatively crowded scene, here we have a much less crowded scene, a more sparsely populated city. We would call this low pressure, we would call this high pressure. We have some other terminology that you'll see throughout this section as we're learning about what it is that goes into making our psychological experiences with sound. And these new terms that we want to introduce are compression and rarefaction. A compression is an instance of high pressure, okay, where we have, again, a number of molecules in a relatively tight region of space, a given number of molecules in a small region of space, and then here we have that same number in a much wider region of space. We call that a rarefaction. So air can be at any given moment comparatively compressed or comparatively rarefied. Okay, so to reiterate, compressions are local regions of high pressure, okay, many air molecules per unit space. Rarefactions are local regions of low pressure, few air molecules per unit space. Okay, there's a mathematical relationship between pressure and intensity. So far, in talking about amplitude, we've made reference to two different units of measure. One is pressure, and one is intensity. And there is actually a very nice and systematic relationship between those two, and it's stated here in number 2. Intensity is proportional to pressure squared. A very simple formula that you might remember is I is proportional to P squared. Let's all say that together and make that a mantra for today. I is proportional to P squared. There you go. Okay? All right, so we'll come back to that at different times. And you'll see that when we're talking about amplitude, sometimes we express this with respect to intensity, sometimes we express it with respect to pressure. Okay, the human ear can respond to a 15 log unit range of intensities. Now remember that the intensity is equal to or proportional to pressure squared. So this is a fairly large unit, and we have the nervous system responding to a 15 log unit range of intensities. Let's see if we can get you to understand that intuitively on a few different levels. First, we can think of a pressure or an intensity that is so soft that your nervous system can't pick it up. Your action potentials will not start, and the neurons are simply not firing because this is a subthreshold stimulus. If we crank up the acoustic intensity, to the next level, it still might be so soft that your nervous system can't pick it up and we don't get any action potentials. If we crank it up one more time, maybe the most sensitive of your neurons begin to respond and we get an action potential or two. If we crank it up again, we get a few more action potentials. If we crank it up yet again, we get even more action potentials. At some point, we might crank it up so far that this neuron can't fire any faster and it's reached its asymptotic level. Okay? Now, what's interesting is we have distributions of neurons that have different sensitivities. We have some other neurons that might be a little bit less sensitive, and they need more acoustic energy, more intensity, before they start firing. But once they start firing, they will respond in a monotonic manner to increases in acoustic intensity. That is, as you crank the intensity higher and higher, you get more and more action potentials. So now we have two populations of neurons, the relatively sensitive ones that will start this relay race, and the ones that are a little bit less sensitive, they start a little bit later. But after we get to an appropriate level of intensity, these are firing full steam ahead. You can imagine still a third population that's even less sensitive than the second population had been. And we're passing the baton to increasingly less sensitive subsets of our neuronal ensemble until at some point we get to the level of activity, of action potential activity, where all neurons are firing full steam ahead. And we can't go any faster than that, any more than that. We can ask what range of physical intensities is necessary to get from the very bottom, when the most sensitive neuron is just starting, to the very top, when the least sensitive neuron is finally firing and firing at its max. That turns out to be a 15 log unit range of intensities of acoustic intensity. Let's remind ourselves what we mean by log units. So as a reminder, a log unit is also called an order of magnitude. In our class, a log unit will imply a 10-fold difference. So 3 log units is a 1,000-fold difference. The number of log units you can think of very easily as being the number of zeros. If we had a 7 log unit change, we'd have a 7-0 change. If we had a 14 log unit change, we'd have a 14-0 change. Okay? So we're going to be talking about the common logs. Some of you might be familiar with the natural log. That's a different kind of logarithmic system, very important in other applications. We're going to keep it at the common log factors of 10. Okay, so let's go to a potential pop quiz question that extends over a few slides. I think you'll find this really interesting. What we're going to do in this exercise and this pop quiz is try to get you to have an appreciation for the 15 log unit range over which your auditory system is responding to acoustic intensities. And we're going to take this relatively abstract idea of acoustic intensity and try to make it a little bit more tangible to you by giving you an example of something that you know very well. You have a lot of direct experience with the weights of different objects. The weight of a thumbtack, the weight of a pencil, the weight of a barbell, the weight of a car, and so forth. So let's see if we can form that analogy in the following way. A thumbtack weighs 1 gram. A Volkswagen Beetle weighs 1,350 kilograms. And if we convert those kilograms to grams, we can say that a Volkswagen Beetle weighs 1,350,000 grams, or if you will, 1,350,000 thumbtacks. So here, you can imagine that we have a scale, and on this side we might have 1 thumbtack, and on this side we might have a Volkswagen Beetle. The scale would tip, okay? The Volkswagen Beetle is going to weigh a lot more. How many thumbtacks would we have to bring those scales into balance? And the answer is that this weighs 1,350,000 grams, or 1,350,000 thumbtacks. Okay? So we're getting some intuitions now about the relative weights of things. Okay, let's assume we want to make a scale that can weigh objects over a range comparable to that of the human auditory system's range of intensities, namely a 10 to the 15th power range of intensities. Okay? On the low end, we're going to have a thumbtack. Okay, that's going to be the softest sound that we can hear, equivalent to the weight of 1 thumbtack. We'll have a thumbtack there on that side. Here's our pop quiz question. How many Volkswagen Beetles will we need to represent the high end? That's 15 log units higher than 1 thumbtack. Okay? And please show your work. I think you'll find this to be a really interesting exercise. It will give you some intuition about this incredible 15 log unit range that you have in everyday life and didn't know that you had. Okay? Okay, let's talk a little bit more about the units of measure that we would employ for referring to amplitude. And you might be very familiar with this idea, the decibel. Most of you have heard about the decibel. It's the unit of measure corresponding to displacement. Remember that a moment ago we talked about displacing air molecules and having moments of compression and moments of rarefaction. We'll talk about just how displaced these molecules are and express it in decibels. The typical unit of measure is really the bell, named after Alexander Graham Bell, who had done a lot of work more than 100 years ago now on the telephone. The bell is a relatively large unit of displacement, so it's typically handier for us to divide that up into smaller units, in the same way that we take a meter and we divide it into centimeters or millimeters as is relevant for us. Typically the bell is a little bit too large to work with, so we divide it into tenths, and we talk about a tenth of a unit as a deci unit, or a decibel in this particular case. And it turns out that, as we referred to earlier, different ways of measuring amplitude. So we're going to express our decibels either with respect to pressure or with respect to intensity. So sometimes we describe the measure of displacement in terms of pressure, and when we do, you'll see the decibels listed numerically, and they will have this insignia next to them, SPL. dB SPL would be the decibels in sound pressure level. Alternatively, sometimes we express the decibels with respect to intensity level, or IL. So when you're reading an article and you're trying to understand how intense is the stimulus in this particular article, you might want to be aware of the decibel nomenclature, and it could be either with respect to SPL or IL. In all cases, though, whether we're talking about SPL for pressure or IL for intensity, the decibel is the ratio of two quantities. Maybe it's two pressures, or maybe it's two intensities. We don't typically mix those two bags of different kinds of units. We talk about two pressures or two intensities, and we look at that ratio. See if we can understand the ratio here. Okay? The decibel formula for two pressures, and we'll only memorize one of these two. More frequently, I think we do use the pressure, but you see the intensity indicator also from time to time. But we'll do the pressure one, and I will ask you to memorize this. So this is dB SPL is going to be equal to the following formula: 20 times the log of some ratio. Okay? And in this case, it's going to be the ratio of two pressures. Okay? The first pressure, which is in the numerator, is pressure X. And what we mean by pressure X is the pressure of the stimulus of interest. The stimulus of interest might be my voice. The stimulus of interest might be a car that's coming toward you. You want to know how loud that car is. You might want to know how loud a jet engine is. That's the stimulus of interest. That becomes your pressure X. We normalize or divide pressure X by some kind of standard pressure. And by convention in the field of psychology, and in other related fields as well, we use a standard pressure of 20 micropascals. So again, Pascal is returning. This is the fellow from Pascal's triangle. And Pascal is the unit of pressure. And we can talk about the pressure that we have, or the force per unit space, is the Pascal measure. And we can talk about 20 micropascals as typically the pressure that somebody your age can hear. When I say somebody your age, somebody in their late teens or early 20s typically can hear 20 micropascals under ideal conditions. People who are younger than you, people who might be 12 years old or even 5 years old, they probably can hear even fewer micropascals than that. People who are my age would need a greater pressure level than that. But for people your age, that becomes a standard. So we make that the standard pressure, and then we divide that into whatever it is that we're trying to measure. The acoustic energy for my voice, or the jet airliner, whatever that might be. We take that fraction, or that ratio, and compute the log of that value, and multiply that by 20, and that gives us dB SPL. Okay? All right, so let's go on to the potential pop quiz question. If our stimulus is rustling leaves that we might hear on an autumn afternoon, okay? If rustling leaves have a dB SPL of 20, that's 20 over on this side, then what must be the value inside of the parentheses? So what does this value have to be inside of the parentheses, such that if we take the log of it and multiply that by 20, we wind up over here on the left also with 20 dB SPL. We'll give you a moment to think that through and see what kind of computation you come to. Okay, so in this particular case, we do have the answer right here. Let's see if we can walk through the answer. Again, the question was, if rustling leaves have dB SPL of 20, then what must the value be inside of the parenthesis? And the answer is 10. Okay? And here's the reasoning. Since the log of 10 is equal to 1, okay? Again, we have 1, 0 here, so the log of 10 is going to be equal to 1. And 20 times 1 is equal to 20, okay? which is the dB/SPL of rustling leaves, then we know that the answer inside of this, or the value inside of this parenthesis, had to have been 10. Okay? So you might imagine then that we had rustling leaves creating a 10-fold increase in sound pressure level. They might have been at 200 micropascals. Divided by 20 would give us 10. The log of 10 gives us 1. 1 times 20 is 20, and this is how we can begin to understand how much pressure is out there in the environment and what the corresponding dB/SPL would be. Hope that one example gives you a feel for how people compute amplitude expressed as dB/SPL. Importantly, the decibel is always a relative measure. As we saw a moment ago, we looked at the relationship between a standard pressure, which people like you can typically hear, 20 micropascals, and some stimulus of interest. In this case, it was rustling leaves. In our class, we'll talk about the relationship between sound pressure levels, dB/SPL. We could have done dBIL, but we'll leave it at dB/SPL for our class. Okay? All right. So that's what we've got on amplitude. Let's now move over and talk about another important feature of the physical stimulus for acoustic energy, or another property of acoustic energy, its frequency. As you know, frequency can be defined as the number of cycles per unit time, typically cycles per second. We might harken back to what we understood in the world of spatial frequencies when we talked about the number of dark light patterns per unit space. Now we've got cycles that are moving through regions of compressed air, or phases of compressed air and decompressed air or rarefied air, and we can ask how frequently those compressions and rarefactions are occurring, not per unit space, but rather per unit time. Okay? So the unit of temporal frequency is, in the American pronunciation, Hertz, okay? In the German pronunciation, Hertz. And you can feel free to use either of those in our class. It might be fun for you to throw in Hertz every once in a while. Okay? So here are two stimuli that differ from each other in frequency. Okay? Stimulus on the left has some regions of compressed air, some regions of rarefied air. Here's the passage of time. The stimulus on the right has similar levels of compression and decompression or rarefaction, but you might see that we're going through the cycles of compressed and rarefied air much more frequently per unit time on the right than we are on the left. Okay? So this one is going to be higher frequency, this one is going to be lower frequency. I want to point out something that I've mentioned before in class, but we want to make sure it's really clear to you here. What we can do is measure the wavelength by looking at any corresponding points on a wave. And so we might start out at the peak and go to the next peak and ask how much time has elapsed here, or if this were space, how much distance has elapsed in this particular case. And we can see that we have a relatively long wavelength here, and we have a much shorter wavelength for our high frequency stimulus. Okay, we can go from this peak to this peak, a relatively short wavelength. From this peak all the way over to that peak is relatively long wavelength. So there's an inverse relationship between frequency and wavelength. We've seen that before. We'll see it again in the next couple of slides. By the way, before we do that, we might ask which will be heard as higher in pitch. You might have an intuition about this, or maybe you don't. Okay? So let's see if we can get the answer here in the next slide. So pitch is the perceptual correlate, or at least a perceptual correlate of frequency. Typically, a good rule of thumb is this. High frequency will correspond to high pitch. Low frequency will correspond to low pitch. And as we alluded to in the last slide, there's this reciprocal relationship between frequency and wavelength, and those are shown here in yellow. Wavelength is equal to speed of sound, which was 343 meters per second, at least in air, divided by frequency. You might notice that frequency is in the denominator here. Okay? And we have wavelength over on the left side of this equation, so there's an inverse relationship between wavelength and frequency. We see that again over here. Frequency is equal to the speed of sound divided by wavelength. Again, wavelength is in the denominator, so there's a reciprocal relationship or an inverse relationship between wavelength and frequency. If you wanted to, you could unpack each of these. We could say that wavelength is equal to speed of sound divided by frequency. Speed of sound is distance divided by time. And then we have frequency unpacked as cycles per unit time. Okay? And whenever we have a compound fraction like this, you might remember from your algebra days that the way that we satisfy that or resolve that is we invert and multiply. And when we invert and multiply through, it turns out that the time components are going to cancel, and we get wavelength equal to distance per cycle. Okay? We can do the same thing over here. We can see frequency is defined as distance divided by time. That's the speed of sound. and that whole quantity gets divided by wavelength, which is distance per cycle, or you can think of it as time per cycle if you like. Either of those would be fine. We'll do the invert and multiply, and the distance terms will now come out, and we wind up with frequency equaling cycle per unit time. Okay? All right. So what we can say then is that in the following graph, we'll have this important negative relationship between the wavelength and the frequency. We'll see a negatively sloped line here. So wavelength is over here. It's measured in meters. Here's the frequency given in hertz. Okay? And the spacing might strike you as it's a little bit unusual. They've used a logarithmic spacing, so we don't have an even spacing here, but we are seeing the numbers shown here in steps of what you might think of as multiples of 5 and 10. Okay, from 500 to 50 to 500 up to 5,000 and so forth. So we have something like a logarithmic spacing on both axes. What's important here is this negatively sloped line. As the frequencies are getting higher and higher and higher, the corresponding wavelengths are getting shorter and shorter. Okay, and that might be fairly obvious to you. One example that I like to think about is middle C. Many of us know middle C on a piano, and middle C on a piano will correspond to a wavelength in air that's about 1.3 meters. So when somebody goes over to a piano and they're plucking on middle C, they're creating a wave, a sequence of compressed air and rarefied air, sequences thereof, that are spanning over a region of space that's about 1.3 meters. Okay? If we go up to the next C, that's an octave higher than that, that distance will cut in half, because the wavelength will cut in half and the frequency will double. Okay, so here's a familiar face to us. It's Fourier, and what we can do is a Fourier analysis on a complex sound. Okay? So the complex sound that we're going to try to build here in the auditory domain is the same kind of complex stimulus that we tried to build back in the visual domain when we talked about the visual square wave. Now we have an auditory square wave, and what we'll show you, really by way of reminder, is that inside of this complicated pattern we have something that's decomposable into sine wave components. Okay, so here we have a very simple sine wave. It's relatively high amplitude, peak to trough. It's relatively low frequency, and we might see that as being fairly obvious here in the space or the time domain. In this case, it's the time domain. We can also do the same stimulus, or represent the same stimulus, over here in the frequency domain. So you might remember that on this axis we have some indicator of amplitude. That might be energy, it might be contrast. We'll call it amplitude. And on this axis we have frequency that goes from low frequency to higher frequency. So we have a simple spike here to show that we have fairly high intensity and fairly low frequency stimulus. If we play the game that we had played a while back when we learned about FAPO in the visual domain, you might remember that we built the square wave by having these odd integer multiples of the fundamental frequency. So in this particular case, we can do the same thing. This might sound familiar to you. We can take a waveform that is 3 times the frequency. So we're going to triple the frequency. You can see this is happening at a much faster oscillation rate than is this. And 1/3 the amplitude. So peak to trough is quite a bit smaller here. Over in the frequency domain, we'll go to a higher level, okay, a higher frequency, but it won't be quite as contrasty, or we won't have quite as much amplitude there. That should be 1/3 that height. It might not actually be that, but you get the picture. And when we combine those two in the frequency domain and we combine them over here in the time domain, we get something that begins to approximate a square wave. And we can add now something that is 1/5 the amplitude but 5 times the frequency, and go up to the next odd multiple. We can go to 7 times the frequency, 1/7 the amplitude, 9 times the frequency, 1/9 the amplitude, and keep on adding those. And as we add higher and higher frequency components, we get better and better approximations of this auditory square wave. So what I'll do now is I'll play for you an auditory square wave. I think it'll come across on the video. We'll see how we do. Out on the internet, we have this. I'll play for you a square wave first, and then at the same frequency I'll play for you the sine wave. And we'll talk in class about how these differ from each other. Here's the square wave stimulus. Okay, that sounds a little bit rough around the edges, kind of like a game show buzzer, although that was a little bit higher than a game show buzzer typically is. Let's now hear the same sound as a sine wave. Okay. So a couple of features might strike you as very apparent. First, the square wave seemed a lot more intense. It also sounded a little bit edgier, a little bit more like a game show buzzer. The sine wave has a bit of a smoother sound. It's a very subjective description, but we're looking for a psychological description because we have already got quite a good physical description here when we're contrasting the smoothly varying sine wave with the square wave. All right, let's take a look at some other frequency-related phenomena. Here's one particular frequency, frequency 1, here's frequency 2, here's frequency 3. We can combine these very simple sine waves to make relatively complicated patterns as we had in the last slide. If we take frequency 1 and we superimpose it, point by point, adding together frequency 1 with frequency 2, we have, I'll do frequency 1 and frequency 3, for example, we get this relatively irregular squiggle. We can then do frequency 1, 2, and 3, and we get, again, a different kind of irregular squiggle. So as you're listening to my voice, it turns out that portions of your auditory cortex are performing something akin to a Fourier analysis, decomposing all of the individual sinusoidal components from the relatively complex wave that's coming to you from my vocal cords. Okay, let's see if we can now move on to the last of our 3 elements in understanding the physical properties of acoustic energy, and this is going to be phase. So finally, when we consider phase, we're talking about the aspect of a wave that pertains to relative position in time or in space. Just to help you review a little bit for the final exam, we talked about phase even in the visual domain, and we introduced a particular type of cortical cell. That cortical cell was called a simple cell, and that was a cell that would fire if the light was distributed in a particular spatial pattern. There might have been an on-center pattern where we have maybe dark, light, dark, and a particular cell might have liked that particular arrangement. That was dark, light, dark. But if we now move that stimulus through, say, 180 degrees of phase, and we have light, dark, light, all of a sudden that stimulus, that neuron, that had been firing will begin to stop firing, or at least reduce its firing rate. So we had these simple cells that were sensitive to spatial position. We'll see if we can understand now this relative position in time rather than in space, but same kind of an idea. Typically we express phase in angular units, so we might talk about degrees of angle. We might talk about radians, for those of you who have had some trigonometry. Here's a diagram relating phase of sine waves to their angular shifts, and we will end on this one. Actually, one more after this one, but this will set up our very last slide. This is a little bit busy, so I'll ask you to stay with me. We're going to start over here. We're going to start at panel A, and as we go around to differently lettered panels, we'll come all the way back, and this will be in the final sequence, panel I. Okay, so we're going to go A through I to go all the way around the circle. We'll ask you to keep an eye on the relationship between what's going on here and this very smoothly, sinusoidally varying pattern that we have. Okay? So here we are at panel A, and we're going to be at this particular point in the sine wave. And I'll ask you to think about this. Imagine that there's an axis over here that corresponds to amplitude. Okay? And at the top of that y-axis, we have compression. And at the very bottom, we have rarefaction. And we can talk about the proportion of compression that we have, or the total magnitude of our compression versus the total magnitude of our rarefaction. That might help us to understand this. Another little bonus that we have on this fairly busy graph is this. We have a layout of the degrees of angle, and we also have a layout of the radians, another measure of angle. So we'll go through 360 degrees as we go from diagram to diagram. Let's start here. Pretend that we have a radius of the circle that we can think of as the minute hand on a clock, and we're pointing to 3 o'clock for the moment. Okay? We're starting right here, so we have neither compressed air nor rarefied air. We're at the point of neutrality here. We're pointing directly over to this 3. I'm now going to ask you to think about moving back counterclockwise by 45 degrees up here in panel B. So we were at 3 o'clock, we're now moving back this way, and we're forming an angle that's 45 degrees if you like degrees, or pi over 4 if you prefer to think in radians. Okay? Now what we can say is that if you were to take the sine of that angle, that would be 0.707, and we move from A to B, so now we're moving in a direction toward compressed air. And in fact, at point B, the air is about 7/10 as compressed as it ever will be in this particular example. If we move back another 45 degrees, now we have a right angle. And we're at 90 degrees, or if you prefer to think of it in radians, pi over 2 radians, and we're at panel C. Fortuitously, we're at C over here, and that's the level of maximal compression. So we got a little bit lucky that the C here happens to correspond just by chance to maximal compression. So now we have really compressed air. And then we're going to move another 45 degrees, and we're over at D, and the air begins to decompress a little bit, still on the compressed side, but decompressed to the sine of 135 degrees, which would correspond to 3 pi over 4. We're going to get a sine value of 0.707, so we're coming back down. Over at E, we're once again at the point of neutrality. Here we are. We're neither compressed nor rarefied. We're at complete neutrality, and we have sine equaling to 0 here. Okay? As we move down to here, 225 degrees, we're over at panel F, and we can see that at 225 degrees, the sine of 225 degrees, or 5 pi over 4, is going to be this minus 0.707. The minus would signify that we actually have rarefied air, and the 7.07 signifies that we're about 7/10 of the maximal rarefication. Down to G, we're at maximal rarefied air, or maximally rarefied air. Okay, that's going to happen now at level G when we're at minus 270 degrees, or 3 pi over 2. Then we're starting to get back toward the compression, though still on the rarefied side for panel H. We're at 315 degrees as we moved counterclockwise almost all the way through. Okay, and we're at minus 0.707 again here, which is where we were a moment ago. And if we move back one more time from there to here, we're now back at I, which is the same as A, and we're back to our starting point. So we've taken 8 different snapshots along the traverse, and we get this nice relationship between the motion in a circular and the sinusoidal motion, and we can understand now relative phase. Okay? So hopefully that's clear to you. I look forward to taking your questions in class on that if that's not clear. But I think most students can see the patterns that are arising in this diagram. Okay, let's see if we can understand what's really neat about phase. First, we can take a look at how these stimuli differ from each other, and they're always going to be phase shifted. Here's stimulus 1. Here's stimulus 2 in dotted line. It has the same frequency. It has the same peak to trough difference, so it's the same in amplitude, but it's just shifted in this particular case by 45 degrees. So the peaks are not lining up one on the next, and the troughs are not lining up. They're phase shifted by some little bit. Here we have a 90-degree phase shift. Some of you who are familiar with trigonometry might recognize the relationship between these two waveforms as being the relationship between sine and cosine, 90 degrees out of phase with each other. This is the one that I think is most interesting in panel C. We have our standard stimulus, if you will, in number 5. Then what we have is stimulus number 6, which is exactly opposite to stimulus number 5. We have a 180-degree phase shift. What's really cool about this is that this is exactly the technology that is used in many noise-reducing or noise-canceling headphones. Some of you may have noise cancellation headphones. Some of you may have driven in a noise cancellation car or a noise cancellation airplane cabin. The idea is that the headphones will first detect what is the background level of noise, what is the background level of amplitude, frequency, and phase. And once all of those have been registered, very counterintuitively, the headphones make things quieter by adding noise. Very counterintuitive. They add noise in a very selective manner. Specifically, they look at the predominant phase that's coming in, and they now introduce an equal but opposite intensity, opposite in terms of being 180 degrees away in phase. So that when these two stimuli add, you might notice that the maximal peak compression corresponds to the maximal, or I should say the minimal compression, or the maximal rarefication. And those are going to zero out. Here they're going to zero out. They're going to zero out at every point along this line. And so when there's zero acoustic energy, we have silence. We have noise cancellation headphones. They get rid of the background noise. Very ingenious idea and counterintuitive, because we make things quieter by adding noise, assuming that the noise is appropriately phased. Okay, so what I'll leave you with is that these phase differences are going to be critical for our ability to localize sounds. And our ability to localize sounds will be the topic of a future lecture. For right now, what I'd like you to do is to continue to work on that pop quiz question about the number of Volkswagen Beetles that we would need to have to correspond to the upper end of the range of acoustic intensities that we can hear. Also, please make note of what you found particularly clear about amplitude, frequency, and phase, and what was less clear. And we'll take those discussions and your questions and comments in class. See you in class.